We have completed Chapter 9, which was Air Standard Cycles. In that chapter, we looked at modeling internal combustion engines, gas turbine engines, and what they had in common was that the working fluid was all an ideal gas, whether we treated it with constant specific heat or variable specific heat. And now we're going to switch gears into Chapter 10. A couple of main things are going to be different about Chapter 10 than Chapter 9. One is that we're going to be covering refrigeration and heat pump cycles, which is sort of like the opposite of power cycles, in which we're transferring heat from cold to hot at the expense of uh, requiring power. Another thing that's different is that the working fluid is not going to be an ideal gas. It's going to be basically a type of a refrigerant, and that can vary from cycle to cycle. So let's go ahead and get started. Let's see what you're going to cover in Chapter 10. Okay, so this module is basically a roadmap and a recap a little bit. And we're going to cover what is a refrigeration and heat pump cycle. I'm going to try to quickly give you how would you analyze the four basic components of the refrigeration cycle in different modules, and then finally go through the basics of how you would analyze a basic real vapor compression refrigeration cycle. So let's see. Here's a recap of going all the way back to Chapter 5. And remember, the quiz question was, what do these three things have in common? What do those things have in common? Well, the answer is they're all systems operating in a cycle. Okay, let's see. They all require some type of electric power to operate. And the other key thing is to recognize that these three basic pieces of equipment, the refrigerator, an air conditioner, and a heat pump, all three of those basic systems are transferring heat from cold to hot. And so we're still recapping Chapter 5. Let's look at that basic schematic, and let's look specifically at a refrigerator. Let's talk about a little bit how a refrigerator works and how would an engineer analyze a refrigerator. Well, in my schematic, my basic schematic, everybody remembers, it's some black box. So it's a system operating in a cycle. Look at my arrow. My block arrow is going counterclockwise. That means that the net power is required to run this cycle. And the result is it enables us to transfer heat from cold, I call it TL, textbook calls it TC, up to T hot, TH. I've tried to draw in a couple little icons to help cement this in your mind. Let's see, what are we trying to do? We're trying to keep, let's say, ice cream or other refrigerated or frozen goods cold, and we're transferring heat up into the surroundings. And so I've drawn a little stick figure that kind of represents you standing in the surroundings. Let's see, remember coefficient of performance for refrigerator, energy sought over the energy that costs. And so without even writing down a formula, you say, oh yeah, that's right. The energy sought, that's Q dot L as shown on the sketch, and the energy that costs is W dot net. And another thing I hope you remember by looking at this basic schematic and looking at the direction of the arrows, you can observe the first law of thermodynamics for any system operating in a cycle, Q dot H minus Q dot L equals W dot net. Well, I just changed the slide and things look very similar, but we're going to review what does a heat pump look like and how does it work? And do you see that the basic schematic, it's the same schematic. This is copy and paste. It's just that the objective is slightly different. And so here's a picture of a residential heat pump, okay? And what we're trying to do here is we're transferring heat from the outside surroundings where it's cold in the wintertime. We're at the expense of we have to invest some electric power, basically to run a compressor. And then we're transferring heat up into the warm space, TH. Well, here's you. Here's you trying to stay warm in your house. And you can see, again, the first law, just visually, look at this. You can see that Q dot H, the energy that you're seeking to put into your house, is simply going to be the sum of what's being transferred from the cold surroundings plus the power required to run this cycle. So you can see that Q dot H is going to be equal to Q dot L plus W dot net. So refrigeration cycle, heat pump cycle, they're basically operating in the same cycle. It's just that the objective is different. So let's review coefficients of performance for both of these types of engineering and familiar equipment. For a refrigeration cycle, energy sought over the energy that cost is Greek letter beta for a refrigerator, coefficient of performance, Q dot L over W dot net. And remember, for a Carnot cycle, if this black box were a Carnot cycle operation, it would reduce down to TL over TH minus TL by way of the first law, and recognizing that for the Carnot cycle, the reversible refrigeration cycle, then the heat transfer is proportional to the absolute temperature of the high and low temperature reservoir. Okay, heat pump cycle. Let's see. Coefficient of performance is gamma, Greek letter gamma for the heat pump. Energy sought over the energy that cost. Well, let's see. The energy is sought. We can figure this out in our heads. It's Q dot H. That's our objective for running a heat pump. Energy that costs, it's exactly the same, W dot net. So therefore, you can kind of remember for a Carnot cycle, heat pump, reversible cycle, you can look at this derivation of the coefficient of performance. And since the Carnot cycle has heat transfer is proportional to absolute temperatures, you've got that the maximum possible coefficient of performance for a heat pump is TH over TH minus TL. It is my hope that you have this not necessarily in your head immediately, but you could quickly get to this out of your head instead of depending on a formula sheet. And there we go. There's my recap. And I thought I had that. So think of your head, think of your brain as a bank, as a memory bank, and what kind of key things are going to be important for Chapter 10. Remembering the coefficient of performance is the energy sought over the energy that costs. You've got that in your head. Also, the basic schematic I hope you have in your head for a refrigeration cycle. And the first law for any system operating in a cycle, Q dot H minus Q dot L equals W dot net. And that's simply a matter of looking at the direction arrows, and with your eyes, you can see how Q dot H must add up to this value plus this value. So do you need a refresher on Chapter 5? You say, well, we covered that, but it seemed like a million years ago. Well, don't forget, you can go back to my Chapter Key Points playlist, and then you can click on any of these Chapter 5 videos that are associated with refrigeration cycles. So let's see, here's an overview of refrigeration and heat pump, refrigeration cycle, heat pump cycle, and and a comparison of all the coefficients of performance and performance measures. So there we go. There's your roadmap of what we're going to cover in Chapter 10. And my claim is you're already familiar with the fundamentals of analysis of refrigeration and heat pump cycles. The devil is in the details, and I'm going to do my best to show you in subsequent videos of how you can attack real honest-to-goodness refrigeration cycle problems, real honest-to-goodness heat pump cycle problems. So there you go. Let's see, in terms of a little preview, I can tell you that as an undergraduate and as a high school student, I had a rough time really understanding how refrigeration cycles work. So I had to work very hard to gain a working understanding of how to analyze those cycles as an engineer. So I hope that helps you get started with chapter 10 because it really is an important chapter as you begin your early experience as a practicing engineer, as a mechanical engineer.